Right, so your first question might be what electric charge really is, or why anything is charged at all. And to the first question, we can accept electric charge as just a fundamental property of matter in our universe. There's not really a greater explanation to that if you get right down to the bottom of it. Just like mass or inertia, just like time, just like our three spatial dimensions, that we often call X, Y, and Z. They just exist. To the second question, why anything is charged at all, we can at least build a mental picture of charged macroscale objects from their atomic makeup. So an atom is made up of even smaller particles, a nucleus that contains protons and neutrons, and that nucleus is surrounded by an electron cloud made up of electrons. Protons have a positive charge, plus E, and electrons have a negative charge, minus E. Neutrons, as you might guess from the name, are neutral, and they contain no net electric charge. The SI unit of charge is the coulomb, same guy as up here, coulomb, and it's often abbreviated with a capital C. And that unit assigns the value of E to be 1.60 times 10 to the negative 19 C. That's very, very, very small, right? But if we're building up macroscale charge from the charges of things like electrons, you may have a lot of them, and they may each just contain a teeny tiny amount of charge, and it can still have a large effect when they all come together. So while some of the understandings about atomic structure are relatively modern, the concept of electricity and charge dates back as early as actually 600 BC with the Greeks. So they may not have known about the atomic structure or all of the details, but they noted that amber could be rubbed with wool to then attract other objects. And because of this, the word electric derives from the Greek word for amber, electron. Electron with a K. So that's kind of interesting. And the attraction they witnessed was due to the fact that two positive charges, I'm going to go ahead and type this out as I talk, two positive charges or two negative charges repel each other, whereas a positive charge and a negative charge attracts each other. This is often summarized with the phrase, like charges repel, opposite charges attract. Go with the nice blue color here, and I'll box this in, because this is kind of the fundamental bit that we build up from. Net charges on a body derives from an imbalance of positively charged protons and negatively charged electrons, right? So if we're not talking about individual particles, but a whole body that contains many, many electrons and other particles, protons, neutrons, I guess, then you're talking about net charge. And often it's the electrons that are transferred between objects to create net charge imbalances. So it's not usually the protons that are kicked out of the nucleus. It's usually the electrons that can conduct through a material to then transfer to maybe another material. And so if you basically have, some material here and it has some number of electrons, and you have some other material over here, and it has some number of electrons, right? They may have the same number of protons to start, right? And they're just distributed evenly, right? But if you were to add up how many negative charges exist and how many positive charges exist, the net charge on these might be 0, right? But if you bring them together and you rub them around, like if one is wool and the other is amber, then these charges can jump from one to the other, and it's usually the negative electrons that are jumping from one to the other. And it comes down to the material properties, which way they transfer. Each material has a different electron affinity, and so if you get one that has a higher electron affinity, or it wants electrons more, then the electrons go towards that one. And so then what you end up with is some net negative on one and net positive on the other, no longer neutral. So that's the general process of how you can transfer charges and how things get to be charged overall in the first place. So this leads to a very important concept within electromagnetism, and it won't be a new concept. It'll just be a new one applied to this electricity thing. So you're familiar with conservation of energy, hopefully conservation of momentum. You learned about these in your mechanics course. Don't panic if you don't remember what that means. This will probably jog your memory. It just, the law of conservation of electric charge simply states that the net electric charge of an isolated system is constant. So, conservation of charge. Net electric charge of an isolated system is constant. So the conservation of energy and momentum, similar thing, just replacing words, right? So isolated system just means, in our example here with red and blue things, those are the only two things that are interacting at that moment, right? So you can either pretend that the rest of the universe doesn't exist and they're just in some void space on their own, or you can just say they're very well insulated from anything else. They're not really rubbing up or making contact with anything else, and so it's an isolated system. Next, we'll talk about Coulomb's law.